All right, so the next thing we're going to look at is shells, subshells, and orbitals. So now what we are going to be focusing on is what's happening inside the atom, outside the nucleus, in the various electron shells that we have. Another name for shells is energy levels, and there's something called subshells, and we'll call them sublevels, and we have orbitals too. We'll go through all three. Now shells are what you guys have studied. These are called principal quantum levels or energy levels. And what I'd want you to understand is something to do with the physics of the atom inside. Yeah, because that'll help us understand many more things going forward. All right, so to understand the physics of the atom, it's important to also understand the nature of electrons. So let's talk about that for a second. And I think, it might seem obvious to people, but it is the foundation on which most of chemistry is based. So what are the nature of electrons? Now, what are electrons? Electrons are negatively charged particles, but they are kind of free to move in an atom. Now, because they're negatively charged and they are free to move inside the atom, they will never be together. They will all repel each other. It's because they are all the same. Now you might wonder, why doesn't it happen to protons that exist inside the nucleus? Well, technically speaking, protons will also repel each other inside the nucleus, but they have another large piece of attraction, a force called the nuclear force. It's a nuclear binding force that holds the protons together. That's a very strong force inside the nucleus. Electrons don't have that. There is no binding force. There's no force inside the nucleus. What it is each individual particle is free to move, and generally they're negative, so they're repelled by each other, but are attracted by what? By the nucleus, because the nucleus is positive. So inside an atom, there is a constant struggle for attraction and repulsion. Remember that first, okay? And then this repulsion that we call electrons repelling each other, you can call it inter-electronic repulsion. Now, you don't have to use the word, but it makes life easier if you can use terms. Inter means between. Inter-electronic means between electronic. So there's repulsion between electrons. There is inter-electronic repulsion. And what happens is, these guys are around the nucleus and they kind of move around in this space. And you might have studied the space as you thought it was called shells, but the space the electrons move around in is called an atomic orbital. So atomic orbitals, let's call it that, are spaces electrons move around in. That's the easiest way to think about. So wherever any particular electron is inside the atom, the space it can move around in is called an orbital. Okay, and we'll talk about that in a bit, but it's unique to each electron. So if sodium has 11 electrons, all 11 of them are occupying different spaces. Okay, some of them are in similar spaces, but mostly are different. Like in hydrogen and helium, there are 1 or 2 electrons. They're also, you could say, they're in some space, and those space that they exist in is called an orbital, not a shell. Then what is shell? If a shell is not the space, what is shell? Okay, now the orbital is the space, and the space you guys have thought about it is in terms of these spaces are in terms of like, if you remember, they either can be spherical or dumbbell shaped, and we'll talk about that in a minute. But we'll go into detail of the shapes also. But when you have elements like, for example, let's take carbon. Carbon is easy because it only has 6 electrons. Well, we know carbon has 2 in the first shell and 4 in the second shell. So this is shell 1 and this is shell 2. And the 6 electrons occupy different spaces, and those spaces are called orbitals. So then, before we get to orbitals, you must wonder then, well, if they are called orbitals, then why do we have shells? What is the point of these shells, really? Okay. Well, honestly, there is a point of these shells. So there is an importance to these. So each of these shells has a purpose. These shells represent distance. Represent distance. Simply that. This distance between electron and nucleus. So no matter what space they occupy, the space could be, hey, what do you mean by space we occupy? I'll give you an example. If I'm in a pool, a swimming pool, going underwater, the space I can occupy is the volume of that cube or cuboid. If I'm in this room that I'm sitting in, the maximum space I can occupy is the size of the room. Right? I'm in bed, the space I can occupy is the size of the bed. And obviously, whatever container I'm in, that's the maximum space I can be in. Let's say I was to go inside a submarine. Now, a submarine's actual space structure is different from a room. A room has corners. A submarine really has no corners. It's a giant tube and it's like a cylinder with curves on either end. So the space I'm in, that I occupy, has its own unique shape depending on the container I am in. So think of orbitals as containers for electrons. Some can be a certain shape and some another shape. Just to get this sorted, just some will be in a shape like this and some will be in a shape like this for now. So out of the 6 electrons in carbon, some are in a sphere and some are in this 2 spheres combined together called a dumbbell shape. But what's more important for the right now is, then Bilal, what are these shells? Like, why do we have these shells? If all electrons are in spaces, why do we care about these shells? Because the spaces occur at each and every shell. Now, what are shells? Shells are basically the distance the electron is between itself and the nucleus. So when we say there are 2 electrons in the first shell, that means there are 2 electrons a certain distance away from the nucleus. And the 4 electrons in the second shell are a certain distance further away than the nucleus. We call them, they are further away. And these 2 are closer. And simply because of their distance, they become these energy levels called shells. Now, the analogy here, and I've said this in my lessons also, is this. Imagine you're living in a house. And right now I'm in a room which is on the first floor or the second level of the house. And I have a certain energy compared to the Earth's center, gravitational energy, right? So anywhere on this second unit of my house, I can move to any room, I'll have the same energy. So my internal energy, gravitational energy, is what determines my shell, like in the sense, my floor. So if I was to go down, I'd be in level 1. So I'd have lower energy. If I'd come up, I'd have more energy. So which floor I'm at is like which shell I'm in. But which room I'm in on each floor is what we call the orbitals, the space they occupy. So I can have a different room on the first floor, a different room on the second floor. They'll have different energies. But if I have different rooms on the second floor, they tend to have the same energy. If I have similar rooms on the first floor, they'll have the same energy. So the floors determine the energy and the space is determined by the orbital. Now you might say, okay, where did this energy come from? Why do electrons have energy? I understand why humans have energy, because the center of the earth is attracting us. While similarly, electrons have energy. Why? Because the center of the nucleus is attracting them. So here, this is what becomes important. Let me add a page here. And so what becomes important is to think about an atom and And I know I'm going a little basic here, but this is important to make sure everybody gets this. So I have a nucleus. What charge is it? It's positive. Okay. Now, before I introduce my nucleus, and let's say there is no nucleus right now, what we scientists have done is, okay, is that if an electron was free, if there's a free electron, what it means is it has got no attractive or repulsive force acting on it. So let's say I call something called free electron. It has no attractive or repulsive force. Okay, let's say I tell you, hey, let's talk about an electron that is free. By convention, electrons are free, but that is not subjected to any other electrostatic forces. Now, all the forces are electrostatic in chemistry. Why? Because they're charged. So now, first of all, before I even talk about this far, what do you think? How many free electrons does carbon have? Let's say carbon has 6 protons, 6 neutrons, 6 electrons. Me telling you a free electron has no attractive or repulsive force. Inside the carbon atom, how many free electrons are there? There are 0 free electrons in an atom. Okay? There are none in an atom. And when they are free, we can say they have 0 energy. So when they're free, they have 0 energy. Now you might say, why am I mentioning this? Well, honestly, so now go back to my atom. So if this is my nucleus, an electron, let's call it E1 and E2. Which of these if I tell you that only one of them is being attracted by the nucleus, which one is it? Now here, what I'm going to explain to you is, what I'm leading towards is you realizing why do certain shells have more energy and why do certain shells have less energy. So if I say only one of these 2 electrons is feeling the attraction of the nucleus, if we had to choose which one would it be, you'd say it'd be E2, because it's close enough, so it's being pulled by the nucleus. But this guy is so far away, we can say it's so far away, it's almost free, right? So E2 is being pulled, E1 is far away, has no energy. So now think about this. Is how you will get the answer yourself. So if I have to move an electron from the position of E2 to the position of E1, would I have to provide any energy or no? Yep, for those of you who thought, yes you do, absolutely. Because there is a force of attraction. So the nucleus is pulling these electrons. So to move this guy out, I have to apply energy. You know why? Because energy is needed to overcome any force, to overcome a force of attraction or repulsion. In this case, electrostatic attraction. So in physics, you probably have done work and energy. So I'm going to move this guy to the left. I tend to do that. So you say, okay, well, energy is needed too. So let's say I tell you, hey, move E2 to E1. You'll say, hey, Bilal, I need some amount of energy. Let's call that energy E2. Oh, okay. Hey, it's the same E. But let's say capital E2. I'm providing energy. Now, according to the law of conservation of energy, if I am providing energy, I am doing work, right? So that means work is being done. The technical definition of physics work, where force is applied over a distance. So a work is being done, but it has to be converted. Converted to what? Now, the funny thing is, you guys have experienced this at the mechanical level. It's like saying, I'm trying to raise a ball in height. It's work done, remember? Now if I were to pick a ball from the ground and bring it up above my head, I am doing work against gravity. But work done against gravity is equal to the gain of potential energy. Remember, gravitational potential energy. So any work I do to pull the ball from the floor to for example above me, I'll require energy. Similarly in chemistry, if I have to do work, if the energy is needed to overcome something, work is being done. If work is being done, it is converted to something. So what that means is, let's say this work done is converted to what? Converted to potential energy. And you might wonder, wait a minute, isn't potential energy due to mass? Well, that is the case if it's gravitational potential energy. This is electrostatic potential energy. So basically, the electron, to go from here to here, the electron has to be, you have to provide energy to get it here. It might have less force. You see, it is almost free, but the energy is high, which is different. Force of attraction is different from energy. So you might think about this. Wait a minute. So you're telling me that the electron E2 is experiencing rate of force, but to make it go from E2 to E1, where it's almost free and I have to provide energy, I'm doing work against attraction. Yes. So all the energy you provide gets converted to potential energy of the electron. Yes. Which means the further away the electron is, it has greater energy. So E2 is closer, more attraction. E1 is further, weaker attraction. But who has more energy? E2. For those of you still confused, think about this analogy. Think of the nucleus as the ground floor, and think about a building, and you in that building either can be on the first floor or the second floor. Have you ever tried walking up? Is walking upstairs easier or walking downstairs easier? Clearly, anybody who's ever walked stairs knows that walking up is harder. Why? Because work is done. And when the work is done by you to go to a higher floor, and this is the Earth's center, let's say, center of Earth. So, if you're closer to the Earth, you are going to feel greater force. But when you go on top, you have more energy. Which is, you might say, wait a minute, doesn't it mean more force, more energy? Well, that's for work done. It's different for particles or individuals. You can do work and that's important. That's important to us. Whenever you do work against a force of attraction, you are moving further away. That's the whole point of doing work against force of attraction. But as you move further away, your own energy increases. Similarly, because that's what happens when you go simply, when you are moving away from, so now, and basically a free electron is you going into space. Think of yourself as Elon Musk. These days he's the fun guy, right? Crazy guy. But now you are in free space. Now, imagine Elon Musk charged, and we know that he charges a lot of money or anybody to launch anything into space. Imagine all the energy these rockets used up. Why do they use up so much energy? Because you are going further and further and further away. So the guy who is in space has almost no force of attraction, no F attraction. But imagine how much energy it must have taken to kick that guy into space. It's like you being on the roof of a building. As you ascend floors in a building, you get to have more gravitational potential energy as you go higher up. But You are further away from the earth, so there's less attraction. So let's say you were to go off into space. The attraction between you and the earth is going to decrease and decrease and decrease to become almost zero. But your internal energy will go high up. Now you might say, well, I don't feel it. Well, potential energy is never really felt. Hence the word potential. It's like you might say, hey, I have the potential of getting an A. Sure you do. But till I see the grade on a piece of paper, the potential cannot be seen. The potential can only be seen by its effects. So I know it's there. If I see a grade, I know it's there. I cannot see your inner potential. Similarly, in physics, you cannot see the potential energy of you being in space. So if you were to be on that space station, what is it? International Space Station, ISS. Is that what it is? I forgot the nickname for it. The International Space Station. If you get on that space station, you have zero attraction from the earth. You are a free electron, but you have very, very high amounts of energy. Because if you were to fall back into earth, you're going to die without protection. Similarly, think of the nucleus as the center of the earth. And this was electron 1 and this is electron 2. The idea was the closer you are, the force is greater. But as you move further away, the guy that's further away has less force, but what? More energy. So technically speaking, which electrons have the most energy? The ones that are free. The ones that you've been kicking out. So technically speaking, when we were talking about first ionization energy, and sodium with its 11 electrons becomes sodium with its 10 electrons, and we know this from last year also from our earlier studies, that the guy kicked out is the outer electron. It's kicked out. After it gets kicked out, it'll have least amount of energy. And that's the whole idea of ionization energies. The outermost are further away, they'll have the most energy first of all, but because they have the most energy, they are kicked out the easiest. So that's why they're all interlinked. When we say that outermost electrons are easiest to remove, you know why? Because they are attracted the least by the nucleus. Therefore, energy required to remove them or make them free, because they already have enough energy, so they don't need too much more. Think of the energy required to become a free electron is like an unlock code, or like you collecting coins and there's a certain limit. The guys that are the furthest away in the outermost shell already have a large loot of those electrons called energy. You just have got to give it more. So that's why it's always easier to remove the outermost, because they already have the most energy. So there's a connection between internal force, easier to remove, attraction. So in an atom, and for the sake of a simplified diagram, let's talk about beryllium, because that guy has only 4 electrons. In its shell formation, we call it 2 electrons in the first shell. So beryllium, nucleus is plus. Let's say the first shell is right here. I'm just taking some basic stuff. So now let's draw them out. So let's say I say there is E1 here, E2, E3, E4. All these 4 are attracted by the nucleus. Okay? So they're all attracted by the nucleus. And let's call this F1 the race, not the race, but the force. F2, F4, F3. So there are 4 electrons inside the atom, and the nucleus is obviously 4 plus. And that 4 plus is pulling all of these. You all got the physics for the force. You all know, obviously, the closer you are, the more attraction. So here, the force 1 and force 2 are greater than force 3 and force 4. Do you all concur with this? I hope you do. Now, tell me something. If I were to ask you, hey, can I make electron E1 move to this position? If I ask you to move electron E1 from shell number 1 to shell number 2, what would you have to do? You might think, okay, well, am I doing, this is how as a physics person I think, well, if I have to move something from E1 from first shell to second shell, I have to overcome a force of attraction, so I have to provide energy. Therefore, there is work done on the electron. Therefore, the energy, so when I move electron from E1 from here to here, energy is needed, work is done, which therefore means if electron goes from the first shell to the second shell, what happens to the electron's internal potential energy? If I were to ask you, and I'm repeating myself, let's say we did the work to move electron E1 from the first shell to the second shell, what will happen to its energy? Its internal potential energy will increase. Absolutely. If you all been thinking increase, absolutely on spot. Now, we've talked about ionization energy, have we not? Now, ionization energy is trying to take E1 all the way out of the atom, making it free. Hence, you require it. Now, tell me, if I want to make E1 free, and I'll delete this now. Okay, so now I'm back to my E1 and E3. Let's say E1 and E3. I want to kick them both out at the same place. I want to take them both out to the same place. And let's call the work done to kick E1 out as W1 and the work done to kick E3 out as W3. The work done. Okay. First of all, we all know E3 is high energy. E1 has more force of attraction. E3 has less force of attraction. But between the two, E1 and E3, first, just tell me, think about this. Between E1 and E3, I want to kick them both out. Right? Which will require more energy to be kicked out? E1 or E3? Clearly E1. It's closer, more force. So I know this, that the work done for E1 is going to be more than the work done for E3. Yep. Now, so, but they all get to the same energy. So let's say E1 needs more money than E3, but they both end up making the same money. Think of energy as money. And the work done is somebody giving you money. E1 was given more money, E3 was given less money. But they both now have the same amount of money. So what does that mean? Somebody started with more money than it is. So for example, let's say, I mean, it's just analogy. Let's say free means having $100. So they both end up having $100, but I had to give more money to E1 to make it $100. What does that tell you about E3? That E3 already had more money than E1. So for example, if I give $80 to E1 to become 100, I probably give $50 to E3 to become 100. Which means E1 already had $20 because 20 plus 80 is 100. But E3 had $50 and I gave 50 more to make it free. So here, that is the explanation why, and that's simply why E3 has more energy than what? E1. Do you follow this? Yeah. Now, tell me something. If I said I have to kick E2 out also to the same space. Now tell me, what can you say about W2 in relation to everything else you've seen? So W2 is the energy required to remove the electron in the same shell as E1. It's the same force of attraction as E1. So it will require the same amount of energy as E1. Same work done. So W2 equals to W1. Yes or no? Yeah. Therefore, deduction says what? That therefore E2's energy is equal to E1's energy. Yeah. Because they both require the same amount of work, which must mean they currently possess the same amount of energy. Which is why this, another name for this is, and a more technical name is energy level. Shells are called energy levels. And why? Because any electron in that energy level has the same amount of energy. What that means is, to kick it out and make it free, it'll have required the same amount of energy and the same work done. And that's important, because therefore they anything on the same energy level is pulled with the same amount of force. So that's why electrons in the same shell have the same energy, the same force of attraction, and the same work done to make them free. That's why these are called energy levels or shells. All right? And I know that there's a lot of drawing here, so maybe if I were to erase all of this. Okay, sorry. No, what did I do? So let's say, just for a minute, I were to erase all of this. Delete. And if I tell you that, hey, I moved my E1 to E3. So when you take electron from a lower energy level to a higher energy level, what does it simply mean? That when an electron goes from a lower energy to a higher energy, you have to do work, which means the electron gains energy. And when the electron gains energy, we call it quote unquote excited. So later on, you'll also hear the term excited state. Simply means excited state is somebody that gave energy and the electron jumped up. Now, the funny thing is, we don't study this in A levels, but that's exactly what happens in fireworks. Fireworks are you providing energy, electrons get excited, they absorb energy, they do work against the force of attraction, go to higher shells or energy levels, and then they come down. So if you think about it, when they go up, you did the work and they absorb the energy. Now when they come down, what will they do with the energy? They'll have to give it out. Most of the time, the energy that these electrons that get quote unquote excited, when they come back down, they give the energy as heat or light or sound, which is why fireworks are hot, they have lightning, and they make a lot of sound. Simply speaking, fireworks are not bombs. They're just pure particles whose electrons we are exciting by lighting that fire, and then they go up and then they come back down. And when they come back down, you see them as the colors of fireworks. All right? That's the origin of the fireworks that we have. It's again electrons jumping between these energy levels, going up by you providing, them coming down, releasing, and therefore you see colors.